Hey there, and welcome. Have you ever been working on differential equations and just wished there was a clever shortcut? Well, you are in the right place. Today, we're going to unlock a really powerful method called exact differential equations. And the best part? It's a fantastic tool that actually connects right back to stuff you probably already learned in multivariable calculus. So let's dive in and see how this all works. So here's our game plan. We're going to kick things off by getting the big idea, which is all about reversing the chain rule. Then we'll jump into the nuts and bolts, the test you have to run, and the step-by-step method. After that, we'll solve a basic example together, look at some trickier problems you might run into, and then wrap it all up with the one key takeaway you'll definitely want to remember. All right, first up, reversing the chain rule. We're about to borrow a really clever trick from Calculus 3, and it's going to help us unlock the solutions for a whole new class of differential equations. Just think about that for a second. We use the chain rule all the time to differentiate complicated functions, right? So what if we could just run that whole process in reverse to find the original function that solves our DE? Well, that is the core idea right here. It basically transforms a difficult differential equation problem into a much more familiar calculus puzzle. And that leads us to the formal definition. An exact differential equation looks like this. Some function m times dx plus some function n times dy equals 0. Now, the key insight here comes straight from vector calculus. If you think of m and n as the components of a vector field, the equation is exact only if that vector field is conservative. And what that really means is that our whole expression is just the total differential of some hidden underlying function. We call it psi. Our entire goal is to find that psi function. So how do we actually do this? Well, that brings us to our next section, the test and method. Think of this as your practical step-by-step toolkit for solving these things. Okay, before you do any integration, before you do anything else, you must run this simple test. You take the partial derivative of m with respect to y and the partial derivative of n with respect to x. If they are equal, boom, the equation is exact, and you've got the green light to go ahead. If they're not equal, you have to stop and use a different method. Seriously, this is the most crucial first step. And here is the 5-step recipe for success. First, you run the test. Second, you integrate m, but only with respect to x. Now, because this is a partial integration, your constant of integration isn't just a number, it's actually a function of y, which we'll call h of y. Step 3 is where the magic happens. You take what you just found, differentiate it with respect to y, and set it equal to n. This is the clever step that lets us figure out that unknown h of y function. In step 4, you solve for its derivative, then integrate to find h of y itself. And finally, you just plug it all back together. And if this process feels familiar, it should. It's exactly how you find a potential function back in Calc 3. All right, theory is great, but let's actually see this thing in action. It's time for a basic example. We're going to put that 5-step method into practice right now. Okay, here's our problem. Notice it's already in that nice standard m dx plus n dy equals 0 form. So our m is the stuff in the first parentheses, and n is everything in the second one. First things first, we run the test. The partial derivative of m with respect to y is just 2x. Easy enough. Now, the partial derivative of n with respect to x is also 2x. They match. So we know for sure this equation is exact, and our method is going to work. Now for step 2. We integrate the m term with respect to x. The integral of 2xy is x squared y. And the integral of negative 9x squared is negative 3x cubed. And of course, we absolutely cannot forget our constant of integration, which is that all-important function h of y. Now, for steps 3 and 4, which we've done kind of behind the scenes here, we would take our result for psi, differentiate it with respect to y, and set it equal to our n term. This lets us solve for that mystery h of y function. And after a little bit of algebra and one more quick integration, we find that h of y is actually y squared plus y. We plug that back into our expression for psi, and there it is, our final solution. So that's how it works on a nice, clean, straightforward problem. But, problems you find in the wild are rarely so neat. So let's talk about handling some trickier problems and watching out for those common pitfalls. What's the #1 most common pitfall? It's not the calculus, it's the simple algebra, especially with negative signs. Let's look at a problem that isn't in standard form to start, where one tiny mistake in the setup can derail the entire solution. So look, the most crucial thing is getting the equation into that m dx plus n dy equals 0 format. Look at the initial form on the left. To get it to the standard form on the right, we have to move that y prime term over to the left side. And when we do that, we have to be super careful and distribute the negative sign, which flips 3 minus x squared y into x squared y minus 3. It's such a small algebraic step, but it is absolutely critical to get right. After you rewrite it in standard form, you'd follow the exact same 5-step process we just did. Once you work through all the integration and differentiation, you get to the general solution. But this is an initial value problem, so we're not done yet. We have one more step. We just plug in the condition they gave us, that y equals 8 when x is negative 1, and that lets us solve for our constant c, which turns out to be 12. And that gives us our final specific solution. Okay, another classic trip-up isn't in the setup, but in the calculus itself. You gotta remember your basic integration rules. For instance, and this one gets people all the time, the integral of negative sign is positive cosine. Let's see where that can pop up. Now, this example looks way more intimidating, right? We've got exponentials and trig functions all mixed together. But don't let it fool you. The process is exactly the same. First, you run the test for exactness, and it is. Then you move on to the integration step. So when we go to integrate our m term with respect to x, that's where our tricky integration comes in. That negative sign becomes a positive cosine. Then, when we take that result, differentiate it with respect to y, and set it equal to n, something really nice happens. Everything matches up perfectly, leaving us with h prime of y equals 0. And that just means h of y is a constant, which gets absorbed into our final constant c, giving us this really clean, elegant solution. Okay, we've walked through the theory, the step-by-step method, and even a few tricky examples. So let's wrap this all up with the single most important idea to take away from all of this. If you remember one thing from this whole explainer, let it be this. The method of exact equations isn't just some random algorithm to memorize. It's a powerful change of perspective. You are literally taking a problem from one branch of calculus, differential equations, and turning it into a search for a potential function, which is a classic and hopefully familiar problem from multivariable calculus. And that leaves us with one last thought. This technique, transforming a problem you don't know how to solve into one you do, is one of the most powerful strategies in all of math and science. So as you continue your studies, keep asking yourself, what other really complex problems out there could be solved maybe even easily if you could just find the right way to look at them?